No, okay. Hey, Year 12, thanks for joining me. Going to be having a look at alkanes today. I'm going to try and keep the lesson short and sweet. My laptop is having technical difficulties, so I'll continue to go through it because my screen's shaking, but I can still write. And today we're going to be looking at alkanes as a family, and we're going to be doing the GCSE bits that just have that little bit extra detail involved in them. Lots of you, if you had me at GCSE, will recognize a lot of these processes. So I'm going to get straight on with it. I'm going to share my screen with you guys. Then I'm going to see if I can, so share screen, go for that one. And then do like that. And then stop my camera, even though the camera continues to run, which is part of the problem. So, okay, you guys can now see my screen. Right. Okay. So today we're doing alkanes. You guys have been practicing your naming, and you should be working through Doc Brown's website a day, and of course that gives you instant feedback on your ability to name and the practice, of course, of naming. So today we're doing alkanes. The learning objectives just gonna takes my laptop a little bit of time. So this is AS Unit 1. Let's go right to the bottom. This was our previous lesson. Let's add in extra notes. So today we're focusing on alkanes as a family, as a homologous series. So learning objectives. Number 1, we need to remind ourselves is no fractional distillation steps. Let's get rid of that. Fractional distillation steps. Now, you learned these steps at GCSE, but now they're going to ask it, and they're going to ask it as a big question, kind of like 5 or 6 marks potentially. Then we need to, after that, we need to talk about understand combustion, again, done at GCSE. But the equations are now going to get asked far more heavily, and they're going to be expecting you to be able to give equations for longer alkanes, which means balancing becomes a bit more challenging. I'm going to put combustion, and I'm also then going to tack on, of course, pollution. I'm also then going to be mentioning be able to draw isomers of alkanes. Specifically branched. I'm actually going to do isomerism in a bit more detail as well when I do that. But I'm just going to crack on since my laptop gives me very limited time in terms of how long it functions for. So, okay. So fractional distillation from GCSE. I don't know why it keeps bringing that up. So frac dis is where we're going to be starting. Oh, can you, I'm just going to, sorry guys, if somebody realized that I haven't got my other laptop up with the YouTube channel up, so I can be able to see your chats. It should, let me get into this pretty briskly. If I go to my channel, I should be able to see, there it is. Whoa, let's mute that. There we go, pause that. Hey, nice to see you, Dinesh. Wow, long time no see. It's nice to see you, Dinesh. Wink it, hey. I've got Julian there, I like it. So fractional distillation, and we're going to be giving our steps, and we know these, of course, from GCSE, so I'm not going to waste your time. I'm here for free education. Good, Dinesh, I'm really glad to see you. It's been a long time. I hope you're doing okay in the UK and you're coping with all this crazy coronavirus stuff and you're keeping well. Okay, so guys, what I'm going to quickly do is we realize that the number of steps we're going to have, and I'm going to give you the first letter just to kind of help you guys. I know it's been a long time since you've done it. So step number 1 begins with V. Step number 2 begins with F. Step number 3 begins with T. Step number 4 is, there you go, S. Step number 5, yeah, again, it comes with B. Right, okay, and I know it probably actually makes it a bit more tricky for some students because they might actually have these steps in their head and not remember what they start with. And of course, my starts here are going to be slightly different from everyone else's. So if you want to just ignore those front letters and have a go at giving me those 5 points, it might actually be 6 by the time we come out with this, then please have a go. Pause the video now, have a go. And then you can mark your own as a result. Okay, so here are the steps. We're going to vaporize vaporize crude oil. Now this is done, vaporized crude oil. This is done at about give or take about 600 degrees Celsius. It does need to be done in the absence of air. There is no air, otherwise they will combust. But we're going to vaporize the crude oil. This is done outside the machine. This is the first step. Second step is we're going to feed vapor, and of course vapor means gas, feed vapor into fractional tower, distillation tower if you prefer, fractionating tower. Right, now I need to say what's special about the tower. The tower has a temp gradient, and then you have to say what the gradient is. So it's hot at the bottom, warm at top, warm top. Next, bigger molecules have higher boiling points. Now, this is the tricky bit. So far, GCSE is exactly the same as this, but now you get your extra mark for point 4. Bigger molecules have higher boiling points. You now need to explain why. Due to stronger van der Waals forces or London dispersion forces, depending on which one you want to use. You can use either. Due to stronger van der Waals forces. Yeah, Edexcel actually prefers London dispersion. AQA prefers van der Waals. Cambridge prefers van der Waals. Okay, so bigger molecules have a higher boiling point due to stronger van der Waals forces. Right. Last point, bigger molecules therefore condense. Bigger molecules condense lower down in tower. And at this point, I'm then just going to remind you, and very rare for A-level, much more common at GCSE, is that they could potentially ask you to do the clever trick of giving you a tower diagram and asking you to give the fractions in order. So in terms of the tower, the vapor goes in, VAP, enters a tower, and that tower is hot at the bottom and warm at the top, not allowed to say cold, and the fractions come out at their different levels. So let's put all of them on. So we've got natural gas, nat gas, sometimes called petroleum gas, petroleum gas sometimes, or liquid petroleum gas, LPG, sometimes called. Then we get petrol, again, sometimes called petroleum, or just gasoline, I've seen gasoline too, followed by naphtha, followed by kerosene, followed by diesel, followed by fuel oil, sometimes called lubricating oil, lube oil, followed by bitumen. So very rare to have it, but every now and again it does appear. Every now and again. Do we have to remember this? Yes. I mean, this is GCSE, Dinesh, so technically, yes, they can ask you to put these in order. They won't ask you to do that. It would be too many questions on a knowledge recall. What they will do is they will just give you with one of these missing and ask you to fill in the blank. So yes and no. They won't ask you to recall them all, but they certainly will ask you to recall some of them. Please note, the majority of these are used as fuels. You do also need to know that some of them have specific fuels. Petrol, of course, is car fuel. Kerosene is jet fuel. Diesel is car fuel. Bitumen is road surfaces. Road surface. Okay. Liquid petroleum gas is household fuel. Does the second one say lub oil? Yes, lubricating. I can add it properly in if you like. Yeah, just lub oil. I just tend to shorten it, make it easy for myself. Lubricating oil. Lubricating oil. There we go. Don't know why I tried to do a bracket. But most of them, naphtha is the only one that stands out here, folks. Naphtha is used in the petrochemical industry. Petrochemical industry. Is naphtha for pharmaceutical stuff? Yes. Otherwise, no, yes, it is. And cracking, Winkit. Yeah, it's a cracking chemical. Oh man, I'm doing this on webinar. Oh, I'm so sorry. It's a cracking fraction. Yeah, petrochemical industry, it just kind of covers pharmaceuticals and cracking for making more petrol. Okay, so those do come up regularly now at A-level. Certainly this one does. This is heavy AS. Heavy AS. This one much less likely, more GCSE really, but still does appear every now and again. Usually only 1 or 2 marks, not many. And you just have to flat out know those guys. It's just a story. You've got to be able to just spit it out on demand. Regular AS in Unit 1. So that covers the fractional distillation process. Covers that. Now I want to talk about, I'm actually going to do this out of order. I'm now going to do some drawing isomerism, just because, you know, these lessons are a little bit dry at the best of times. So nice for me to do a bit of isomerism. Now, isomerism, once again, you did at GCSE, but you didn't do it in anywhere near the level of detail that you need for AS. So the first thing we need to do is we're going to subdivide isomerism into 2 separate families. And these are the S's of isomerism. You will never write these words down, ever. If you are, you're wrong. The first type is structural isomerism. Now, structural isomerism will be defined. You'll be asked to define this. Molecules with same molecular formula, same molecular form, but different structural form. You'll be asked to define them, structural formulae. The next one is stereo. You'll never write that word down, stereoisomerism, but they will ask you to define it. Yeah, molecules with. Now you learned these 2 molecules. Winkit, can you do me a really big favor? There's only 3 people watching, which means I'm currently missing Dixon. But can you also just send a message to the other class as well, just saying that I'm doing a webinar on isomerism and alkanes. They haven't seen the alkanes lesson yet, so definitely worthwhile them seeing it. Definition of molecules with, and by the way, you learn these two together as a pair, because where one ends, the other starts. Molecules with same structural formula, but different arrangements different arrangement of atoms in space. So those are the 2 definitions that you're going to be asked for in isomerism. The next thing is, well, why don't we ever say these ones? Why don't we ever say these words? These words are never written down, just defined. Will they be having another lesson now? Probably bio. Oh, that's probably why. I agree. Yes, well remembered. Thanks, Julian. So why wouldn't we ever say this? The reason being is these are subdivided. Stereo is split into 2 and structural is split into 3. So I'm going to put a little squiggly line down the middle to separate these 2. So structural is split into chain or branched. Now you'll notice chain or branch isomers. Now can I just point out that I'm giving you both words here, folks. The reason being is I've seen Edexcel be their most unreliable specification or unreliable example that I've ever seen. They like to do these questions, and they've given both of these words. And so what that means is I just think it's better routine to give both words. Just put chain/branch, isomerism. Yeah, the next one is position. Positional isomerism, ISO. And then the next one is functional. Now you're going to need examples of all of these. So I'm going to focus on these now first. Okay, so let's see, by the way, the next thing is that all three of these are considered comparative isomerism. What that means is you need two people. You can't just state which one this is without having a pair. Yeah. So for example, let's now focus on chain and branch. Two questions. So you can put a chain / branch isomerism. And we can do, number one is this one here. Let's just stick with this. Let's go for same molecular, C4H10. Right, there are two chain / branch isomers. Lag, question mark? Do I have lag? Oh, that will be a bit of a nightmare if I do. Dinesh, how are you getting on? Is it all okay? Maybe you can just give me a bit of a heads up if it's working all right. It's fine. Okay, cool. Okay, so notice that they've got the same. This is the molecular form. Yeah, molecular form, formulae. Yeah, so what chain or branch isomers are there? Now, guys, I'm going to give you a heads up. There's two. Can you pause the video and can you draw me the two? So the question would be, draw both branch / chain isomers. Now they can do either of those words, isos. I'm just going to put isos instead of isomers. Okay, pause it, have a go. Okay, here's the answer. So the answer to this is very simple. We've got number one, a straight chain isomer. And you can make the note that that's what that is. This here is the straight chain isomer. Kind of makes sense. And this is partly why this is technically the chain or branch isomer. You can have a straight chain. This is one of the one of the chain or branch isomers. Yeah, people think that they just mean a branched one, but no, that still qualifies. That's number one. Let's give the structural of that. Right. What's the other one? The other one is a branched isomer. What I have now done, I have changed the chain length. I have changed, and once again, pause the video. Can you name the two isomers, please? Name the two isomers. Okay, so the two isomers names. The two isomers names. This one is straightforward butane. I think most people will have. And this one, of course, is methyl 2-methyl propane. Now, since Dinesh is in the room and I haven't taught him in a while, it's nice for me just to say, Dinesh, that you technically don't need the two, but I prefer it. The reason why I prefer it, Dinesh, is because most students will lose the mark if they forget a number, because they don't realize when they don't have to include it. But you can never be penalized for including a number. So as long as the number's correct, and that's 2-methyl propane. Those are the two branched isomers. Let's go for another question on this. Let's go for the next question. Let's make the molecule bigger. C5H12. Okay, guys, question. Draw all branched isomers. Draw all branch isomers. Right, guys, this will take you a little bit longer. I need it. I am different exam board. Ah, right, fair enough. Okay, so draw all, pause the video, have a go at drawing them all. Again, this is very common at A level. So here are the answers. I've got 5 C's in a row. There's my straight chain. Isomer number 1, where I always start. Isomer number 2, add a branch. Add a branch. The next question, by the way, I'm actually got a routine to this. So I have gone routine steps. I have gone number 1, straight chain, straight C isomer. Then I've gone add a branch. Then I'm going to go move branch, question mark. Move branch. Can I move this to a different carbon? And the answer is no, I can't. The reason being is that is the same ice. These two are the same. Yeah, I'm just looking at it from a different direction. So that one does not count as another isomer. It's the same one. Okay, so since I can't move it, can I add another? Add another branch? Question mark. Can I do that? Let's take another carbon off and move it. And it goes in the middle, remember, folks. I am just going to do a little reminder. Please do not put benzene chains. Yeah, it's very common that students will do this. Yeah, I've added a branch. That's the same thing, folks. That's still straight. 2,2-dimethylpropane. Absolutely spot on, Winkit. Well done. Good answer. So how many isomers were there? There were 3 for that particular one. For this one here, there is 1, 2, 3 branch or chain isomers for C5H12. So really interesting question. Now, what you'd hopefully realize is this doesn't seem like an awful lot. And can A-level make it more challenging? And the answer is God, yes. They really can. And it's amazing what they can do. Let me show you. Same question, folks, but now much harder. C5H10. I don't know why I put a dot on it. Right, now you'll notice I've done something very subtle. I have changed the number of H's. What that means is that all of a sudden, I'm going to have a different molecule, and I'm going to have probably an alkene. Now, I'm going to give you a very specific question here. Draw all branch/chain isomers. Yeah, there's your question. Guys, this is much more challenging. Pause the video, draw them all. See if you can get them. Good luck. Okay, answer. Much more challenging. Now, I actually need to make the, I need to be careful here because the branch chain one is the tricky bit. So what I'm now going to do is I'm going to go, right, 5 carbons. And this time it's a H10, which means I'm an alkene. Now, I could be a functional isomer, which we'll come to in a minute, which is a cyclo. But that would be a functional isomer, not a branch or chain. Would cyclo? No. Winkit. Yeah, well done. Good question. The reason being is it becomes a functional isomer. Wouldn't be a branch or chain. What I'm going to do is I'm actually going to draw what they would actually do is in reality in this exam is they would actually give you that one. They would give you pent-guanine, and remember you must include the number now in that name. We have left GCSE behind. Hola, hi Donna, nice to see you. So they're going to give you this molecule. They're going to give you pent-guanine. They'll probably ask you to name it first. Yeah, there's pent-guanine. And they will say, draw all branch and chain isomers. So let's now have a look. So the first thing I'm going to do is, right, I have to change the chain. So the first mistake students make is that. That is not a branch or chain isomer. That is a position isomer. I have moved the double bond, giving me pent-2ene. I am still a pent, which means this is not a branch or chain isomer. I have not changed the main stem chain length, which means that one is incorrect. I'm going to re-put that there, and I'm going to go, no, incorrect. So now what I need to do is I need to break someone off and put it in the middle. So I'm going to take him, and I'm going to break him off, and I'm going to put it here. Count my sticks on. All my sticks must go on. There we go. So that's the first one. Now, the fascinating thing about this question is because the double bond's there, it adds in a whole load of other isomers. Step 1, add a branch. Step 2, can I move it? And the answer is yes, I can. I can now move it to here. So this one here is 3 methyl, 3-methyl butene. This one is 2-methyl butene. That is another branch isomer. I know that if you compare the two of them, that's positional, but those two are both branched isomers of the original pent-1-ene. Right, next question, can I move it anymore? No. If I move that to here, it'll become pent again. So that's not correct. So now, can I add another one? The answer is, can I do that? If I move that, can I put it here? Can I? No, I can't. If I do that, I'm going to have too many sticks on there. Could I move it to anywhere else? Hang on a sec. So I can't move it because I'm going to have too many bonds. But could I move the butene? The answer is I can. I could move that one there, and I can now put this one here. It's so easy to do. There we go. There's another one. So this is 2-methyl butene. Can I move it anywhere else? No, because if I move that to there, it then becomes the same thing from a different direction. So that's now my final one. So it's much more challenging because you start, Dana, don't you have bio? So it's much more challenging question once these enes start appearing. The next thing is, so now that we've done branch or chain, which we can tick off, we can now talk about positional. And we can do all those clever questions for positional. Now, of course, our other families are now going to appear. So positional isomerism. So now all we're going to do is move somebody. That is it. We're just going to move somebody. So I can now give you an example that they will. And they're going to give you somebody like this guy. Yeah. And they're going to say, in fact, let's make it longer. I'd like to think that you guys are all practicing your naming. I'm just listening to the YouTube. Oh, yup, but bio's just going through a PowerPoint. Okay, so I'd love to think that you guys can all name this. Pause the video, have a go at naming it. Answer, 2-chlorobutane. Next question, do I need the number? The answer is yes, I do, because I can have 1 chloro. And in fact, there's my position. So I can now move that chloro into a different position. Notice the stem has remained the same. It is still a bute. Yeah, I haven't changed. The most common mistake is that students will now start branching them, but you're not allowed to. Yeah, you need to stick with the idea of the only thing I can change is the number in front. The main stem must be consistent for positional isomers. Let's look at one that's a bit more tricky, shall we? Let's look at one that's a bit more tricky. Let's do this guy. I'm going to ask Dana, are you there? I wonder if you're in sync with me. Is she there? I'd love to think she was. The problem is if people are pausing it, then they're going to be out of sync with me. And of course, that does put a problem there. But right, so let's name this one. So this one is going to be, again, pause it, have a go at naming. So this is now going to be pent. Is it an ane or an ene? It's an ane, all single bonds. My screen has just started to shake. So it's a pentane. But now I have another family. Yeah, this is pentan 2-one. It's a ketone, is this family? It's a ketone. So now that we've got your ketone, what we realize is, can I move it? What is the positional isomer of this? The positional isomer, there is one and only one, is this guy. Now, it's super common for students to make a mistake here. That now, of course, is pentan 3-one. A very common mistake is for students to move it to the end. You can't do that, because if you do that, you change the family. Yeah, that now becomes pentanal. Very common, not allowed. That's pentanal. Yeah, if you want one L, if you like. Julian, be careful. You've done a normal thing. Look at the name you've done. Pentuone. Nice. Very, very common mistake there. I don't know why it happens. Students like to call these things pentuone. That's super common, and they will lose the mark. The reason being is they've lost the ane. You cannot forget that part of the name. Be careful. I shouldn't actually get rid of it. I should keep it. That's pentuone. No, wrong. That is not okay. You've lost the an. Yeah, telling you, because you can have pentinone. Yeah. Thank you very much, Winkit, for fixing it for me. Do appreciate it. So nice to talk about position isomers. Not complicated. You've just got to be careful because there are all these kind of clauses in there that cause students trouble. So we can tick off position. Right, now we get to functional. So, okay, so this one, of course, functional isomerism. I will add this up here. Functional isomerism. I'm going to make my pen a little bit thicker at this point. Let's go for that one. Functional isos. So, okay, now guys, this one didn't show up. Nice. Oh, thanks to Nash. Made that disappear. So, functional isomerism. So, in this particular one, we realize that if you move things around, you're going to change the family, but they now specifically want you to change your family. So what I now teach here is that certain families you need to put together. So number one, so we learn, number one, alkenes. Let's draw one. Everyone have a go at naming it, please. Alkenes and cycloalkanes. These families now go together. Because what I can do is I can change a an ene into a cycloane. So those families now go together. It all adds up C3H6. Next, family number two. Family number two is ones and als. Ones and als. Let's draw one. So we've got propanone. Propanone versus propanal. Propanal. There we go. Again, two different families. Very important there, folks. The next family to know, the next one, number three, so I can zoom in over there, is alcohols, and ethers. Now, this family is an old family, folks. You never need to name these. No naming, but you do need to be able to draw them. Ethanol, our good old Friday night molecule. Here's ethanol. We can put the O in the chain. So these families you've just got to know. In reality, they can ask you almost any other family. But these three seem to be the best at being able to give people the best skills to be able to attack any other families. So those are things to just know. Now, this is where I'm moving around the atoms in order to be able to change the family. That's what I'm doing here. Okay. So now that we've covered functional, I'm actually not going to cover stereo today. Stereo is split up into geometrical, which is AS, that's AS chemistry, and optical is A2. So don't worry about optical just yet. But you do need geometrical, and I'll be covered in alkenes later on in this, in a webinar. Okay, so going back to my learning objectives, I'm drawing isomers of alkanes. We've covered that. We've also covered general isomerism. I do just want to link one of these isomerisms to the fractionating tower. So one of the things that you guys have to know in terms of boiling point, so boiling point, one of the things that you guys have to know is that if you have a straight chain isomer such as pentane, and you branch it, you compare it to its branched cousin, what we notice is there is a discrepancy in the boiling point of about 5 degrees. So for every branch, reduce BPT, boiling point, by give or take 5 degrees Celsius. So if pentane has a boiling point of around about, well, butane is bangs flat 0. Pentane's about, it's about 20 degrees Celsius. This one's going to be about 15 degrees Celsius. And the last one, of course, dimethyl propane, is going to have a boiling point of about 10 degrees. That's about 10 degrees. So it has the lowest boiling point of all the isomers. Cool. It's just nice to mention that. It comes up a lot. So I'm just going to go back up to here. Check my learning objectives with my laptop being slow. So draw isomers of alkanes. It's nice to also put consider BPT. Consider boiling point. Right. We now need to cover combustion. And again, heavy GCSE. Okay, so subtitle of combustion. Subtitle of combustion. So we know number 1, burning, the common name. Number 2, requires oxygen. Remember, any element ending in gen or ene is therefore O2. And our products. So, question mark. So what products are we going to get? We realize that combustion is split into 2 families. Combustion is either complete. How do you ensure complete combustion? Excess oxygen. Or incomplete. Which one of these, which that means insufficient oxygen, which one produces more energy? Of course, complete. Bigger energy output. That's why we like complete. Yeah. Now, they often put this into context. One of the example questions from a few years back that they gave was the idea that on Everest, helicopters can't fly above a certain height. And above a certain height on Everest is called the death zone. And the reason why it's called that is because in order to hover, in order for a helicopter to hover, they're going to need to be burning fuel with an energy output great enough to be able to hover at that particular spot. Now, jets get over this by flying very quickly in one direction, which pushes air into the engine. But helicopters don't have that choice. If you want to hover, they need to be able to suck air into the engine. And when you get to a certain height on Everest, there is no longer sufficient oxygen to have complete combustion in order to enable a helicopter to be able to sit stationary and therefore pick people off the mountain who are in trouble. And it's all to do with energy output. All you said was there is less oxygen at higher altitude, therefore combustion is incomplete, therefore less energy output, unable to hover. That was all they wanted. Now, these 2 families, I'm going to move that. Don't really want it there. These 2, one of them is divided into 2 additional groups, and that's incomplete. Incomplete is subdivided into incomplete producing carbon monoxide gas, which we remember as being toxic, and carbon solid, which are particulates, which cause global dimming. Particulates, which is global dimming. Global dimming. Global dimming. So When they ask you for these questions in the exam, they're going to be really specific. They're going to be giving you questions similar to this. Write the equation. Write the equation. You now all know, of course, that word equations are dead at A level. Don't even bother. They're dead. Write the equation for the incomplete combustion nice one. Combustion of butane to produce a toxic gas. So they're telling you in the question which route to take. And of course, we always know that we get water. So we've got C4. By the way, molecular kind of disappears out the window at A level as well. Everything becomes so much harder. CH3, CH2, CH2, CH3, plus O2 goes to CO and water. We always make water in combustion. And then you just have to balance it. 4 carbons, 10 hydrogens, oxygen, 4, 9, add 4.5. 4.5 O2s. And we're done. So very common, and it just takes a bit of practice, but they do ask these heavily. Really, really heavily. I also now have to mention other people in combustion. So other elements and combustion. So what other elements are going to take the appearance? Of course, it's going to be number 1 is sulfur. If you see sulfur, then you're going to produce SO2. Sulfur plus oxygen goes to SO2. Sulfur dioxide, an acidic gas, causes acid rain. It causes acid rain because the SO2 reacts with water to produce H2SO3, sulfurous acid. Weak acid, much less dangerous than sulfuric. If you see nitrogen, if you see nitrogen, you're probably, brackets N, you're probably going to get N2 plus O2. You're going to form NO2. Balance the equation. There we go. And that pretty much ends what you need to know for combustion. This also contributes towards acid rain. The NO2 reacts with water and oxygen to produce HNO3. You also actually form nitrous. That's actually nitric acid. It's quite unusual that you usually actually tend to form nitrous acid and NO. I think it's actually a complicated set of equations, and I won't bother to run you through those. But you tend to form nitrous acid rather than nitric acid. I shouldn't really have mentioned that. If you're interested, look it up on the internet. But otherwise, you don't really need to know that one. But that one, you certainly do. Right, now, since my computer is having a heart attack, I'm going to leave you at that point, guys. We have covered combustion. I will post on our classroom. I will post the booklet on alkanes. Also, you've already got that hyperlinked into your document. So please have a go at some of the alkane questions. But year 12, it's been great to see you guys. I hope it makes sense, and I hope you're all doing okay and keeping well. I am worried about you guys. Just look after yourselves. Stay in touch. If you ever need a chat, just give me a call on Google Hangouts. I'm always happy to chat to people. What I'll do is I'll switch now to camera, just so I can say goodbye. I'll start up my camera. I'll go to that one there. There we go. Right, guys. I hope you guys have a nice rest of your evening, rest of your day even. Take care of yourselves. Have a nice weekend. Look after yourselves. Stay well. And I'll see you guys Monday. See you later, guys.